Good afternoon, class. We are looking at Chapter 4, Application of Derivatives, Section 4.2, How Derivatives Affect the Shape of a Graph. So we covered Section 4.1, Maximum and Minimum Values, and now Section 4.2, How Derivatives Affect the Shape of a Graph, reminding everyone of various differentiation formulas from the definition to basic rules. Trigonometric functions, exponential functions, logs, product rule, quotient rule, composite function resulting in the chain rule. And now, when we look at the graph, we can see that delta y is the rise along the curve, and dy is the rise along the tangent line as we go from point P to point Q. dy is f prime of x times dx, and sometimes it can approximate that. Also, if you write the equation of a tangent line at a comma f of a, is known as linearization. Linearization refers to finding the tangent line at a specific point, and then we call it L of x. Recall local or relative extreme values. Extrema is the plural of the Latin extremum. Local minimum occurs at a point C in an open interval of A to B in the domain if f of C is less than or equal to f of x for all x values in the open interval. A local maximum is the maximum value within some open interval. Local maximum occurs at a point C in an open interval of A to B in the domain if f of C is greater than or equal to f of x for all x values in the open interval. So as we look at these two graphs, clearly local mean, local max, the peaks are considered the local max, the valleys are considered local mean, minimum. Absolute, also known as global extreme value or extrema, are either maximum or minimum points on a curve. Absolute minimum occurs at the point C if f of C is less than or equal to f of x for all x values, not in some open interval, for all x values in the domain. Whereas absolute maximum occurs at the point C if f of C is larger than or equal to f of x for all x values in the domain. So if we look at these two graphs, local mean, local max, local mean, local max, local mean, local max, this local minimum is also absolute minimum, because no other point has a smaller y coordinate. This local max is also absolute max because no other point has a larger y coordinate. Definition of a critical point. A critical number or point of a function is a number C such that f prime is 0 or does not exist. So the process would be find f prime of x, set it equal to 0, also where f prime doesn't exist. Those values are critical points. Also, extreme value theorem, also known as closed interval method, where f of x is a continuous function in the interval of A to B, a closed interval of A to B. The methodology is, number one, go through this process and find critical points. Number two, evaluate the function at the end points A and B, as well as the critical points that this process gives you. Finally, absolute maximum is the largest value, absolute minimum is the smallest value. Four point two summary, how derivatives affect the shape of a graph theorem. A function is increasing where f prime is positive, decreasing where f prime is negative. So if we look at these two graphs, This is a curve, and in your mind, assume this is a line. You can see a line with a positive slope, therefore increasing. If you assume this is a line, which is not, of course, it's a line with a negative slope, therefore decreasing. A critical point, as it was mentioned, C of a function is a point for which f prime is either 0 or does not exist. A relative maximum or relative minimum is a critical point at the top or bottom of an interval of a graph, peaks and valleys. A function is concave up, where f double prime is positive. In other words, f prime is increasing, looking like that. It can hold water. That's what we said in pre-calculus stuff. A function is concave down, where f double prime is negative. In other words, f prime is decreasing, looking like that. So it can hold water. And an inflection point C is a point where concavity changes. Inflection point occurs where f double prime is 0 or f double prime does not exist. So this is concave down. This is concave up. This is where the change takes place, known as IP, short for an inflection point. So concave up, the graph of f of x lies above all its tangent lines on an open interval. Concave down, the graph of f of x lies below all of its tangent lines on an open interval. So if you draw just one tangent line, you can see this is concave up, or this is concave up, because it's above the tangent line. On the other hand, this is concave down. When you draw it, it's below the tangent line. Same thing here. So if we do several tangent lines, in this case, more specifically, we are just doing two. You say f double prime is positive, means concave up, means f prime is increasing. And I want to discuss this part. So it's clear that it's above the tangent lines. So if you compare this one to this one, this tangent line has a positive slope. Definitely this one has a positive slope too, but this one is steeper. And the slope for this is larger than this. So f prime is getting larger. F prime is increasing. In this case, both of them have a negative slope. This is steeper. This is more negative times than this one. So f prime is increasing. On the other hand, if we look at this case, so when f double prime is negative, it's concave down. F prime is decreasing. If you look at this case, positive slope, okay? But my apologies, negative slope, this is steeper, so it's more negative. On the other hand, positive slope, and this one has a larger slope than this one. So f prime is getting smaller or decreasing. Now, as far as the inflection point is concerned, a point P on a continuous curve f of x is an inflection point if f of x changes concavity. As you can see, this is concave down, then it becomes concave up. This is the point of inflection. Or this is concave up, then concave down. That's a point of inflection as well. Steps to curve sketch. In addition to pre-calculus steps, we know the pre-calculus steps, and I'm going to discuss it in a moment. Aside from that, we find relative extreme or relative minimum and maximum, and intervals where the function increases and decreases. And so set f prime equal to 0 and solve for x and make a sine graph. For inflection points, set f double prime equal to 0, solve for x, and make a sine graph. Put all of them together. And sketch the graph. All right, extreme values of a function are created when the function changes from increasing to decreasing or from decreasing to increasing. So as we look at this graph, first it's increasing, then it's decreasing. So it gives rise to a peak, an extreme value, more specifically, local max. On the other hand, this is decreasing first and then increasing. So it gives us a value, an extreme value, more specifically, a local minimum. And we can see it with more graphs, decreasing, increasing, decreasing. The change would be local mean, local max. This one increasing, decreasing, increasing, decreasing. And there are changes. This one would be local max, local mean, local max. So in short, as it changes from increasing to decreasing, it's a local max. As it changes from decreasing to increasing, it's a local mean. So a function is increasing where f prime is positive and it's decreasing where f prime is negative. Now, the proof for that is by the mean value theorem that we normally go over it in calculus. You're not responsible for it, but what is a mean value theorem? F is a continuous function in the closed interval of a to b, and f is differentiable on an open interval of a to b. Then f prime of c, what's f of b minus f of a over b minus a. Please understand, this is a closed interval. When we write an interval, we must write from small to large. So a is smaller than b. A is on the left side, b is on the right side. So what does that mean? It means if you happen to have a curve, connect the endpoints A and B, and draw a line becomes a secant line. There is somewhere in between, some point in between that the slope of a tangent line is equal to that. In other words, here's A, so this point has coordinates A, f of A. Here's B, it's B, f of B. If you connect them, this line, which is known as a secant line, obviously has this slope, f of B minus f of A over B minus A. And because it's a continuous function in this closed interval, somewhere in between A and B, for example, C, we will have a tangent line which has the same slope, meaning what? It's parallel. So the two are parallel. So if we do the cross product here, everybody, if I put a 1 here and I do this one and this one, it results in this. So also increasing means for f of x, as x gets larger, then y gets larger. And remember, the interval goes from small to large. B is larger than A. So if f prime is positive, that means anywhere here between A and B, f prime is positive. So that means f prime of c is positive. That means this expression is positive. So if f of b minus f of a over b minus a is positive, and we know b is larger than a, that means b minus a is positive, then f of b minus f of a is also positive. Therefore, that gives rise to this concept of an increasing function. When b is larger than a, f of b is larger than f of a. That's what this means. What is the first derivative test? Y prime equals f prime larger than 0. As we mentioned, curve is rising. When it's negative, the curve is falling. As the change occurs from increasing to decreasing creates a local max. Now, if it's the other way around, everybody, which means first the curve is falling and it's decreasing, then it becomes increasing. So first decreasing, then increasing. Again, it creates a local extremum, but this time is a local minimum. We also have to look at y prime or f prime does not exist. So we set f prime equals 0. We said f prime does not exist. And those are possible local maximum or minimum. We use sign graph for this test. We have the concavity test and we have the second derivative test. And what are those? We take the second derivative y double prime or f double prime. Curve is concave up if it's positive. Curve is concave down if it's negative. So where f double prime or y double prime is 0 doesn't exist, those are possible inflection points. So a function is concave up where f double prime is positive, meaning f prime is increasing, and it's concave down where f double prime is negative, meaning f prime is decreasing. And you use a sign graph for this test. Second derivative test. We have the critical points by setting f prime equals 0 doesn't exist first. Then we evaluate f double prime at those critical points. CP is short for critical points. And we are interested in the sign. It either becomes positive or negative. If it's negative, then graph is concave down, looking like that. So this must be local maximum. On the other hand, if it's positive, graph must be concave up. If the graph is concave up, that must be local minimum. So that's the second derivative test. Now to graph, I want to remind you of a couple of theorems. The end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. Remember, a polynomial is in the form of a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way to a sub 0. This is called the leading term. This is the constant. So everything depends on the leading term. In other words, eventually, when x becomes extremely large or small, this is the one that gives us the shape of the graph. So what happens is that if we are dealing with even power versus odd power, and we have a leading coefficient, this number, positive versus negative. If it's positive and we are dealing with even power, the end behavior looks like y or f of x equals x squared, meaning whether x goes to negative or positive infinity makes no difference. F of x goes to positive infinity. On the other hand, if a sub n, the leading coefficient is negative, it looks like minus x squared. So whether x goes to negative or positive infinity, in both cases, f of x goes to negative infinity, meaning in this case, the end behavior gives us the first and the second quadrant, in this one, third and fourth quadrant. However, if it's odd power, then it looks like either y equals x cubed or minus x cubed. Looks like x cubed. If a sub n is positive, that means x goes to negative infinity, so does y or f of x. Remember, f of x is like y. If x goes to positive infinity, f of x goes to positive infinity. On the other hand, if a sub n is negative, looks like minus x cubed. X goes to negative infinity, f of x goes to infinity, and x goes to infinity, f of x goes to negative infinity. In this case, the first and the third quadrant, in this case, the second and the fourth quadrant. That's the idea. The next thing I want to add is the theorem known as behavior near a zero with multiplicity m. Zero is x minus c to the power of m. When we say zero, it means the root of the function. It means the x-intercept. If m is odd, f crosses the x-axis at c0. If it's even, f doesn't cross the x-axis at c0. So in this case, as you can see, we have the multiplicity that is odd here, even here. The higher the multiplicity, the flatter the curve is at the zero. The sum of the multiplicity is the degree of the polynomial function. See, in both cases, they cross, but this is flatter because this number is larger, but nevertheless, odd means it can't cross. We want to graph y equals x cubed minus 3x squared plus 4. And the reason I'm giving you also in this format, because it makes it easier to see the intercepts, that's the reason. Otherwise, you have to work on it and make it so. So I just wanted to make sure that it's fairly nice and easy to graph. So first thing first, I am going to graph this just using pre-calculus. In other words, you have enough information that you can graph this. But what happens with the calculus becomes more precise. To do so, I notice that I have three intercepts. This one gives me negative 1, 0. This gives me positive 2, 0. And this gives me, again, this format is easier than this format. If x is 0, you get 4. Please understand you can get from here or there. And of course, this one has multiplicity. I'm going to call it M2, which means it can't cross. So if you wanted to graph just using that information with the fact that this is the leading term, that gives you the end behavior. And so negative 1, 0, 2, 0, 0, 4. You can pick a few more points if you want, or just if you graph it just the way it is. This is the end behavior. As it hits this one, it can't cross because the multiplicity is 2. That's why it's a good practice to go the arrow goes up and it has to come back down at some point. And that's good enough for pre-calculus. The difference is we don't know where is the point of inflection, when and where it's going to come back. Is this somewhere here, the peak, the local max, or is it here? Or is it there? We have no idea. We can find it with the calculus. Other than that, we already have an idea how it looks like, okay? So we have the intercept. Let's find critical points to find relative extrema. Critical points, we're going to differentiate. We get 3x squared minus 6x. And we want to do the first derivative test. We want to find the critical points. We're going to set this equal to 0. To do so, we take the 3x out. Times x minus 2. So the critical points are either at 0 or 2. The first derivative test requires a sign graph. The sign graph is a number line from negative to positive infinity. At the bottom, you put x. At the top, you put the function that you want to evaluate. In this case, it's f prime of x. And you put these numbers from smallest to largest. So at x equals 0, f prime is 0. At x equals 2, f prime is also 0. Now you pick up test points. What are test points? Well, to the left of 0, for example, -1. Between 0 and 2, for example, 1. After 2, 3, 3,000. So just any number that is in the interval of interest, because you have now 1, 2, 3 intervals, or sub-intervals, I should say. So you plug in minus in, you plug in 1, you plug in 3 into y prime and evaluate it. For example, if I plug in -1, again, -1 squared, which is positive 1 times 3, minus 6 times -1, positive 6, they add up to 9. And it's positive. Now, before I do the rest of them, please understand, because this one has exponent 1, which is odd, this has exponent 1, which is odd, they will alternate. If any of them has exponent even, they will not. So if this one is positive, this is negative, this is positive. But anyways, if you plug in 1, you get -3. We are interested in the sign. If you plug in 2, you get positive. Again, doesn't matter, positive 9 or 9,000. So that means positive, negative, positive. And what is the effect of that? Let me erase my work. I'm going to throw in arrow up for positive, arrow down for negative, because I want to make it clear that as it goes up, arrow up increasing, arrow down decreasing, which means the function is increasing from -infinity to 0, union 2 to infinity, and decreasing from 0 to 2. Also, as it changes from increasing to decreasing, this is a local max. As it changes from decreasing to increasing, this is a local mean. So if the x coordinate is 0 for local max, you put it back into the original equation. When x is 0, we already know the answer is 4. So we say local max is 4 at 0, 4. On the other hand, this is where local mean happens, because arrow down means decreasing, arrow up means increasing, plugging 2 into the original function. Again, it happened to be one of those pairs. Local minimum is 0 at x equals 2 or 2, 0. And so, again, where is it increasing? Here and here, meaning from -infinity to 0, union 2 to infinity is increasing. Here is decreasing from 0 to 2. We're going to continue with the same example class. This is the function. Okay. This is the derivative. These are possible extrema. Remember the critical points. Now, the second derivative test, you find f double prime or y double prime and evaluate it at these critical points. If it's positive, concave up means relative mean. If it's negative, concave down means relative max. So differentiate. Again, 6x minus 6. That's the first. Part B evaluated at CP. So that's part A. Now part B, plug in 0, you get negative. What matters is the sign. So if it's negative, we are here. If it's negative, it's concave down. If it's concave down, looks like this. So this is the location of a local or relative max. So if 0 is the location of a local max, what is the a pair? You have to put it back into the original equation. And of course, you get 0, 4. You already have the answer. So graph is concave down, CD concave down. 0, 4 is a local max. If I plug in 2, I get positive. Again, it doesn't matter, positive 6 or any other number. The fact that it's positive. When it's positive, it's concave up. When it's concave up, as you can see from the graph, it's a local or relative mean. So that means, again, you plug it back into original function. You already knew that graph is concave up. 2, 0 is a local minimum. So what happens in a matter of relation to the first derivative test? The second derivative test gives us half of the information. What information it doesn't give us? It doesn't give us intervals of increasing, decreasing. Don't use this for graphing. What is it good for? It's really a wonderful tool for applications. You'll see it later on. So we want to learn that, but you don't have to use it for graphing. So we're going to continue with the same example. Here's the function. Here's y prime. Here's y double prime. We want to find inflection points. That means set f double prime equal to 0, make a sign graph. Because we already found this y double prime from the previous page, we're going to write it. Otherwise, we have to find that. And again, when f double prime is negative, it's concave down. When it's positive, it's concave up. I'm reminding you of that. And so we are going to set this equal to 0. X becomes 1. We draw a number line from negative to positive infinity because we want to test the one. This is a possible inflection point at x equals 1. We're going to go from negative to positive infinity for x. So we are going to throw in this number 1. At 1, f double prime is 0. So again, we use a test point TPs, short for test points. Obviously, to the left of 1, the easiest would be 0. To the right would be 2. So if you plug in 0 into the y double prime 6x minus 6, you get negative. And you put negative. On the other hand, if I put number 2 as a test point, I get positive. Again, the key being negative versus positive. It doesn't matter, how, what number. In other words, negative 6 or negative 6,000, it has the same meaning. So first and foremost, because of the change, it doesn't matter negative to positive or positive to negative. This is the point of inflection. Secondly, negative means concave down from here to here, from negative infinity to 1. Concave up here from 1 to infinity. So concave down in this vicinity, negative infinity to 1, concave up in this vicinity. And as I mentioned, the inflection point at x equals 1. What is the pair? Put it back into original function. This is easier than this one. 1 plus 1 is 2. 1 minus 2 is negative 1 squared, positive 1 times 2 is 2. So 1 comma 2. IP at x equals 1, because the concavity changes, the pair would be 1 comma 2, everybody. Now we want to graph. So what I'm going to do, I'm going to go to the next page, and all the information that we have found so far, I'm going to write all the information. Here's the function. Here's y prime. Here's y double prime. Here's the intercept. Here's where the function is increasing, where the function is decreasing. Here's concave down, here's concave up, here's the IP inflection points. We're going to make a summary table. So we're going to write the pairs that we found here. And starting with the first x-intercept at -1, 0, we are here. The y-intercept is at 0, 4 here. Also, we know it's the maximum. That means we're going to draw a double arrow, meaning as the graph hits it, it can't cross it. IP, the inflection point at 1, 2, somewhere here. Another x-intercept at 2, 0 here. And that's a minimum, which means again, double arrow, meaning as we hit that, we have to bounce back. Do you have more points? Not really, but if you pick x to be 3 and plug it into this again, 3 plus 1 is 4, 3 minus 2 is 1, squared is 1, 3 comma 4, that's another point. And you already know the leading term is x cubed, so you have the first and the third quadrant as the end behavior. So as this is the end behavior, you hit this point, comes to this one, but it has to bounce back. This one continues over here. It has to bounce back. This goes through it and looks like that. Notice we have all the intercepts, the 2x intercepts, the y intercept. We have the inflection point, which means before that, concave down, after that, concave up. We also can see the graph is increasing here, and decreasing in between. So detailed information of the graph can be seen from this drawing.